You know, what happens when you take two of the most powerful technologies on the planet, quantum computing and artificial intelligence, and you smash them together to solve one of the biggest roadblocks in science? Well, that's what we're talking about today. We're diving into a new AI model that has actually learned how to clean up the incredibly messy, error-prone world of quantum bits. Right. So we're always hearing about the wild promise of quantum computers. Designing new life-saving drugs, creating materials we've only dreamed of, maybe even breaking modern encryption. So it's a fair question. If they're going to be so powerful, why aren't they already running our world? Well, the answer comes down to one simple, frustrating word: errors. To really get at the core of this, just think about the difference between your laptop and a quantum computer. A classical bit is basically a light switch. It's either on or it's off. It's simple, it's stable, it's reliable. But a quantum bit or a qubit, well, that's more like a spinning coin. It can be heads, it can be tails, or, and this is the magic part, it can be a weird quantum mix of both at the same time. Now, that's what makes it so powerful, but it's also what makes it unbelievably fragile. I mean, the slightest vibration, a tiny change in temperature, any little bit of noise from the outside world can just knock that spinning coin over and completely corrupt your calculation. And the level of perfection we need here it's just staggering. I mean, to do something truly useful, like breaking a common encryption key, we need our error rate to be something like 1 in a trillion. Right now, our best physical qubits have error rates somewhere around 1 in 100, maybe 1 in 1,000 if we're lucky. That is a massive, massive gap we need to close. So where do we even start? Well, this brings us to the first part of the whole solution. We have to build a kind of safety net for these fragile qubits. We need a system that can catch these errors the moment they happen, before they completely derail everything. And that strategy is called quantum error correction, or QEC. The whole idea here is just redundancy. Think about it this way. If I send you a text that says, hello, you immediately know I meant to type hello, right? Because the mistake is just obvious from the context. Well, QEC does something kind of similar. It takes the information of one perfect, ideal, logical qubit and spreads it across a whole team of many physical qubits. That way, if one of them messes up, the rest of the team can work together to protect the correct information. Now, the most promising way we know how to do this today, the one that everyone is really focused on, is something called the surface code. The basic idea is you arrange your important data qubits in a grid, and then you stick these special checker qubits in between them to constantly monitor their neighbors for any sign of trouble. So here's how it works. It's this repeating cycle. These stabilizer or checker qubits are constantly checking in on the data qubits around them. And when one of those stabilizer's measurements suddenly flips from what it was a second ago, boom, that's a red flag. It's a signal that an error has probably happened on one of the qubits right next to it. And these flipped measurements start to create a pattern of clues all across the grid. But, and this is a really big but, just seeing those red flags is only the first step. Knowing where the errors are happening is not at all the same as knowing what the errors are or how to fix them. And that is the incredibly difficult job of decoding. This pattern of red flags has a name. It's called the error syndrome, and you can think of it like a bunch of confusing clues left behind at a crime scene. The decoder's job is to step in and play detective. It has to look at this whole mess of clues, the syndrome, and try to work backward to figure out what original crime or what original error was the most likely cause so it can then apply the right correction. But believe me, this detective has an incredibly tough job because real-world quantum noise it's a mess. You've got stuff like leakage, where a qubit gets so excited it jumps into an energy state that isn't even a 0 or a 1 anymore. And then you have crosstalk, where messing with one qubit accidentally causes errors on its neighbors. Most of the traditional decoders we've built are based on these nice, clean, human-made models of noise, and they just get completely fooled by this complex, real-world chaos. And this is where our AI hero finally enters the story. Researchers developed a totally new kind of detective called AlphaQuibit. It's a machine learning model, and it completely flips the script. Instead of trying to create a perfect model of the noise, it just learns how to deal with the messy reality by looking directly at the evidence. The way they train AlphaQuibit is honestly brilliant. It's a two-step process. First, there's pre-training. This is like our detective studying billions of old case files from a generic textbook full of simulated errors. It learns all the fundamental patterns of the crime. But then comes the really crucial step, fine-tuning. It gets a small batch of real data from the actual quantum computer it's going to be working on. This is like the detective finally walking the beat, learning all the specific quirks and weird tendencies of their own city. It becomes a true expert on that one device's unique noise. Okay, so the theory sounds great. The training method is clever. But how does this new AI detective actually perform when it's faced with a real case? Well, it was time to put AlphaQubit up against the best decoders in the world. And the testbed for this showdown was none other than Google's Sycamore quantum processor, one of the most advanced systems we have. The researchers basically ran a bunch of experiments, let errors happen, and then fed the clues, the error syndromes, to AlphaQubit and all the other top decoders to see who was best at solving the case.
And the results? Well, they're pretty stunning. On what's called a distance 5 surface code, a pretty complex setup, AlphaQubit achieved a logical error rate of just 2.748%. Now that number might not mean a lot by itself, but look at the competition. The previous best decoder, a super complicated method using tensor networks, came in at 2.915%. Other powerful methods were even higher. AlphaQubit didn't just hang with the best. It set a new state-of-the-art record on real, live hardware.
Okay, great. But can it scale? What happens when we imagine even bigger, more complex quantum computers in the future? Well, the researchers ran simulations of a next-generation distance 11 code, an even bigger, more robust setup. And AlphaQubit's advantage actually got bigger. It beat the next best competitor by about 25%. This shows that its data-driven approach gets even more powerful as the problem gets harder. This thing is not a one-trick pony. So let's zoom out for a second. What does a win like this, an AI-powered victory, really mean for the bigger picture? What are the real-world implications for the future of quantum computing? Okay, here's the bottom line. First, higher accuracy means higher efficiency. A better decoder means you need fewer physical qubits to build one stable, protected logical qubit. That is a huge deal. Second, this is a total paradigm shift. Because it's data-driven, it just adapts to whatever messy noise a machine has. So engineers don't have to spend years trying to perfectly model it first. And here's one last really cool feature. Its output isn't just a simple yes or no. It's a probability, a confidence score. This means we can tell it to just flag and throw away the results it's least sure about, which makes the whole computation even more reliable. Now, let's be real. This isn't the end of the story. The road to a truly fault-tolerant quantum computer is still a long one, and there are major hurdles left. AlphaQubit still needs to be scaled up to even larger systems. It needs to get a lot faster to keep up with the hardware in real time. And so far, it's only been tested on memory experiments. The next big step is teaching it to handle errors while the computer is actually, well, computing. But this breakthrough really does feel like a pivotal moment. It shows us that the very tool we hope quantum computers will one day make better, artificial intelligence, might actually be the key that unlocks their power in the first place. It really leaves you with a fascinating question, doesn't it? Will the road to practical quantum computing be paved not just with better hardware, but with smarter and smarter AI?